We've covered congestion control, which works within network protocols, traffic shaping, which is a high-level network tool, and now we'll look at content distribution, an internet-wide tool that enables websites and network operators to deliver data quickly and efficiently.
And to wrap up this section of the course, your project will explore TCP and its slow start state.
In this lesson, we'll talk about the web and how web caches can improve web performance. We will study in particular the Hypertext Transfer Protocol, or HTTP, which is an application layer protocol to transfer web content. It's the protocol that your web browser uses to request web pages, and it's also the protocol that the responses or the web pages or the objects that are returned as part of a web page are returned to your browser. Your web browser makes requests for web pages, and the pages and the objects in the page come back as responses. HTTP is typically layered on top of a byte stream protocol, which is almost always TCP. A client sends a request to a server asking for web content, and the server responds with the content, often encoded in text. The server maintains no information about past client requests. Thus, we say the server is stateless. Let's take a quick look into the format of HTTP requests and responses. Let's first take a look at the contents of an HTTP request. First, there's the request line, which typically indicates, first, a method of request, where typical methods are GET to return the content associated with the URL, a POST, which sends data to the server, and a HEAD request, which returns typically only the headers of the GET response, but not the content. It's worth noting that a GET request can also be used to send data from the content to the server. The request line also includes the URL, which is relative, and maybe something like index.html, and it also includes the version number of the HTTP protocol. The request also contains additional headers, many of which are optional. These include the refer, which indicates the URL that caused the page to be requested. For example, if an object is being requested as part of embedded content in another page, the refer might be the page that's embedding the content. Another example header is the user agent, which is the client software that's being used to fetch the page. For example, you might fetch a page using a particular version of Chrome or Firefox, and the user agent informs the server which client software is being used. Let's take a look at an example HTTP request now. You can see here the request line, and here are some headers. Accept indicates that the client's willing to accept any content type, that it would like the content to be returned in English, that it can accept pages that are encoded in particular compression formats. We talked about the user agent, so in this case it's a Mozilla 5.0 browser. Here's the host that the request is being made to. This is particularly useful in cases where a particular web server IP address might be hosting multiple websites on the same server. As a quick quiz, which HTTP header field indicates the client software that's being used to make the request? Accept encoding, GET, user agent, or host? Please pick the best answer. The user agent field in the HTTP request header indicates the client software that's being used to make the request. Let's now take a look at the anatomy of an HTTP response. A response includes a status line, which includes the HTTP version and a response code, where the response code may indicate a number of possible outcomes. 100 response codes are typically informational. 200s indicate success. So an example, 200 response code is a common server response that indicates OK. 300 response codes indicate redirection. For example, a 301 response code indicates that the page is moved permanently. 400s are errors, a well-known one being 404, which is not found, and 500s indicate server errors. Other headers include the location, which may be used for redirection, the server, which indicates server software, allow, which indicates the HTTP methods that are allowed, such as GET, HEAD, and so forth, content encoding, which describes how the content is encoded, for example, if it's compressed, content length, which indicates how long the content is in terms of bytes, expires, which indicates how long the content can be cached, and last modified, which indicates the last time the page was modified. Let's take a quick look at an example response. Here is the status line indicating the HTTP version number and a response code, OK, the date the response was sent, the server that served the request, some cookies that are used to set some state on the client, for example, whether or not the client is logged in or not, when the page expires, when it was last modified, and some more instructions about how the page can or cannot be cached. There's also a content type header to indicate that the response is coming back in HTML format. Now, early versions of HTTP actually only had one request or response for every TCP connection. On the plus side, this is simple to implement, but the main drawback is that it requires a TCP connection for every request, thereby introducing a lot of overhead and slowing transfer. First of all, we need a TCP three-way handshake for every request, and TCP must start in slow start every time the connection opens. This is exacerbated by the fact that short transfers are very bad for TCP because TCP is always stuck in slow start and never gets a chance to actually ramp up to steady state transfer. Also, as TCP connections are terminated after every request is completed, the servers have many connections that are forced to keep TCP connections in time wait states until the timers expire, thus resulting in additional resources that the server needs to keep reserved even after the connections have completed. So a solution to increase efficiency and account for many of these drawbacks is to use something called persistent connections. In persistent connections, multiple HTTP requests and responses are multiplexed onto a single TCP connection. Delimiters at the end of an HTTP request indicates the end of a request, and the content length allows the receiver to identify how long a response is. So the server actually has to know the size of the transfer in advance. Persistent connections can also be combined with something called pipelining. In pipelining, a client sends the next request as soon as it encounters a referenced object. So there's as little as one round-trip time for all referenced objects before they begin to be fetched. Persistent connections with pipelining is the default behavior in HTTP 1.1. To improve performance, clients often cache parts of a web page. Caching can occur in multiple places. Your browser can cache some objects locally on your very machine. Caches can also be deployed in the network. Sometimes your local ISP may have a web cache, and later we'll also look at how content distribution networks are a special type of web cache that can be used to improve performance. To see how caching can improve performance, consider the case where the origin web server may host the content for a particular website, but it's particularly far away. Now, we already know that TCP throughput is inversely proportional to round-trip time, so the further away that this web content is, the slower the web page will load, both because latency is bigger and because throughput is lower. If instead the client could fetch content from the local cache, performance could be drastically improved by fetching content from a more nearby location. Caching can also improve the performance when multiple clients are requesting the same content. In this case, not only do all of the local clients benefit from the content being cached locally, but the ISP also saves costs on transit because it doesn't have to pay to keep transferring the same content over these expensive links. Instead, it can simply serve the content to the clients locally. To ensure that clients are seeing the most recent version of a page, caches periodically expire content based on the expires header that we already saw. Caches can also check with the origin server to see whether the original content has been modified. If the content has not been modified, the origin server would respond to a cache check request with a 304 or a not modified response. Clients can be directed to a cache in multiple ways. One is with browser configuration. So you can open your browser and explicitly configure the browser to point to a local cache so that all HTTP requests first are directed through the local cache before the request is forwarded to the origin. In the second approach, the origin server, or the service hosting the content, might actually direct your browser to a cache. This can be done with a special reply to a DNS request. We can see these effects, for example, when we do a DNS lookup for google.com. The response returns a number of IP addresses, and when I ping the IP address, we see that the resulting IP address is only 1 millisecond away, which indicates that that server is not far away, but is in fact very likely on the local network, probably even the Georgia Tech campus network in this case. As a quick quiz, what are some of the benefits of HTTP caching? Reduced transit costs for the local ISP, more up-to-date content, or improved performance for local clients? Please check all that apply. Web caching can reduce transit costs for the local ISP by preventing every HTTP request from needing to go to the origin server. Because the content's also closer to the client, clients should also see improved performance. Let's now talk a little bit about Web Content Distribution Networks, or CDNs. We'll first talk about what a CDN is and why a content provider might want to use one. We'll then talk about how server selection works in CDNs and how clients get redirected to the right server. So first of all, what is a content distribution network? It's an overlay network of web caches that's designed to deliver content to a client from the optimal location. Now, in many cases, optimal means geographically closest, but sometimes optimal is not the geographically closest cache, and we'll see some examples of when that's the case. CDNs are made of distinct, geographically disparate groups of servers, where each group can serve all the content on the CDN. These CDNs can often be quite extensive. Here is a global map depicting the deployment of the Google cache servers around the world, as mapped in a recent project by researchers at the University of Southern California. As you can see, these web caches can be quite extensive, and in many cases there's a concerted effort to place caches as close as possible to users. Some CDNs are owned by content providers, such as Google, and others are owned and operated by networks, such as Level 3, Limelight, and AT&T. Still others, such as Akamai, operate independently. Non-network CDNs, such as Akamai and Google, can typically place servers in other autonomous systems or ISPs. The number of cache nodes in a large content distribution network can vary. For example, in the Google network, the USC researchers found that there were about 30,000 unique front-end cache nodes. As of about 2 years ago, the Akamai Edge platform reported about 85,000 unique caching servers in nearly 1,000 unique networks around the world in 72 countries. Operating a CDN presents many different challenges, and the underlying goal is to replicate content on many servers so that the content is replicated close to the clients. Yet this leaves many open questions, including how to replicate the content, where it should be replicated, how clients should find the replicated content, how to choose the appropriate server replica or cache for a particular client, and how to direct clients towards the appropriate replica once it's selected. This problem is commonly known as server selection, and this problem is sometimes called content routing. Let's take a look at each of these problems in a little bit more detail. The fundamental problem with server selection is determining which server to direct the client to. One could do this based on a number of criteria, such as the least loaded server, the one with the lowest network latency, or simply to any alive server to help provide fault tolerance. Content distribution networks typically aim to direct clients towards servers that provide the lowest latency for the reasons that we talked about before, since latency plays a hugely significant role in the web performance that clients see. Content routing concerns how to direct clients to a particular server. One might do this in a number of ways. One could use the routing system, for example, Anycast. So one could number all of the replicas with the same IP address and then rely on routing to take the client to the closest replica based on the routes that the internet routers choose. Routing-based redirection is simple, but it provides the service providers with very little control over which servers the clients ultimately get redirected to, because the redirection is at the whims of internet routing. Another way to do redirection is application-based. For example, by using an HTTP redirect. This is effective, but it requires the client to first go to the origin server to get the redirect in the first place, increasing latency. The third and most common way that server selection is performed is as part of the naming system, using DNS. In this approach, a client looks up a particular domain name, such as google.com, and the response contains an IP address of a nearby cache. Naming-based redirection provides significant flexibility in directing different clients to different server replicas. So in summary, routing-based redirection is simple, but it's very coarse. Application-based routing is also fairly simple, but it incurs significant delays, which operators really care about, as well as users. Naming-based redirection provides fine-grained control, and it's also fast. Let's take a closer look at how naming-based redirection works. In the example shown here, I've looked up Symantec.com from two different locations. You can see that when we look up the domain name, we don't get an A record immediately, but rather we get a C name or a canonical name, which tells us to look up the following domain name in Akamai. When we look up that domain name, we see two corresponding IP addresses. Notice that when we perform the same lookup from Boston, we also get redirected to Akamai through the C name, but we get two different IP addresses that are presumably more local to the Boston area. So depending on where the client looks up the domain name, it receives different IP addresses at different locations in the network. This is how operators use DNS to redirect clients to nearby replicas. As another example, you can see when I ping youtube.com, I get very low latencies. And when I do a reverse lookup on this IP address, I in fact see that the content is hosted on Google's CDN. It turns out that content distribution networks and ISPs have a fairly symbiotic relationship when it comes to peering relationships. CDNs like to peer with ISPs because peering directly with ISPs where a customer is located provides better throughput, since there are no intermediate AS hops and network latency is lower. Having more vectors to deliver content increases reliability. And during large request events, having direct connectivity to multiple networks where the content is hosted allows an ISP to spread its traffic across multiple transit links, thereby potentially reducing the 95th percentile and lowering its transit costs. On the other hand, there are other good reasons for ISPs to peer with CDNs. First of all, providing content closer to the ISP's customers allows the ISP to provide the customers with good performance for a particular service. For example, you could already see that Georgia Tech has placed a Google cache node in its own network, resulting in very low latencies to Google, and thereby happy customers. You can imagine that providing good performance to popular services is a major selling point for ISPs. Another reason that ISPs like to peer with CDNs or host cache nodes locally is to lower their transit costs. You can imagine that if there were huge demand for a particular video on YouTube and all of the requests and responses were going over expensive transit links, then the ISP's costs would be potentially prohibitively high. On the other hand, peering with a CDN or hosting a local cache node prevents all of that traffic from traversing expensive links, thus reducing costs. As a quick quiz, why do ISPs want to peer with CDNs? Lower transit costs, better security, better performance for its customers, or more predictability? Please check all that apply. ISPs typically want to peer with CDNs to lower their transit costs and to provide better performance for their customers. CDNs don't inherently provide better security or more predictability, and in fact, some ways of redirecting clients to servers may actually reduce predictability. Okay, we're now going to talk about BitTorrent, which is a peer-to-peer content distribution network that is commonly used for file sharing and distribution of large files. Okay, suppose we have a network with a bunch of clients, all of whom want a particular file, and the file might be particularly big. Now, those clients could all fetch the same file from the source or the origin, but the problems with that, of course, are that the origin may be overloaded, and the act of making this request for a large file from the same location on the network may also create congestion or overload at the network where the content is being hosted. So a solution is to fetch the content from other peers, rather than having everyone fetch the content from the origin. We can take the original file and chop it into many different pieces and replicate different pieces on different peers in the network as soon as possible. So the idea is that each peer is assembling the file, but it's assembling it by picking up different pieces of the file. And then it can retrieve the pieces that it doesn't have from the remaining peers in the network. By trading different pieces of the same file, everyone eventually gets the full file. The idea is that hopefully we'll be able to assemble the entire file at the end by the time all the clients have swapped. BitTorrent has several steps for publishing. First, a peer creates what's called a torrent, which contains metadata about the tracker and all of the pieces of the file in question, as well as a checksum for each piece of the file at the time the torrent was created. Now, some peers in the network need to maintain a complete initial copy of the file. Those peers are called seeders. Now, to download a file, a client first contacts the tracker, which provides this metadata about the file, including a list of seeders that contain an initial copy of the file. Next, the client starts to download parts of the file from the seeder. Once the client starts to accumulate some initial chunks, hopefully those chunks are different than those that other clients in the network that are also trading the file have. At this point, clients can begin to swap chunks. As clients begin swapping distinct chunks with one another, the idea is that eventually, after enough swapping, everyone gets a copy of the complete file. Clients that contain incomplete copies of the file are called leechers. The tracker allows peers to find each other, and it also returns a random list of peers that any particular leecher can use to swap chunks of the file. Previous peer-to-peer file sharing systems used similar swapping techniques, but a problem that many of them faced and which BitTorrent solved is called freeloading, whereby a client might leave the network as soon as it finished downloading a copy of the file, not providing any benefit to other clients who also want the file. BitTorrent's solution to free riding is called choking, which is a type of game theoretic strategy called tit for tat. Choking is a temporary refusal to upload chunks to another peer that is requesting them. Downloading, of course, occurs as normal, but if a node is unable to download from any particular peer, it simply doesn't upload to that peer. This ensures that nodes cooperate and eliminates the free rider problem. If you're interested in the game theory behind why this strategy ensures cooperation, I encourage you to go read about the repeated prisoner's dilemma problem, where a tit-for-tat strategy, such as that which is shown here, ensures cooperation among mutually distrustful parties. One of the problems that BitTorrent needs to solve is ensuring that each client gets chunks to swap with other clients. If all of the clients received the same chunks, then no one would want to trade with one another and everyone would have an incomplete copy of the file. To solve this problem, BitTorrent clients use a policy called rarest piece first. Rarest piece first allows a client to determine which pieces are the most rare among clients and download the rarest pieces of the file first. This ensures that the most common pieces are left to the end to download, and that a large variety of pieces are downloaded from the seeder. Additionally, a client has nothing to trade, and it's important to get a complete piece as soon as possible. Rare pieces are typically available at fewer peers initially, so downloading a rare piece is initially maybe not a good idea. So one policy that clients use is to select a random piece of the file and download it from the seeder. In the endgame, the client actively requests any missing pieces from all peers, and redundant requests are canceled when the missing piece arrives. This ensures that a single peer with a slow transfer rate doesn't prevent the download from completing. In this lesson, we will talk about distributed hash tables, which enable a form of content overlay called a structured overlay. We'll talk about a particular distributed hash table called CHORD and an underlying mechanism that enables it, called consistent hashing. CHORD is a scalable, distributed lookup service. A lookup service is simply any service that maps keys to values. Examples of lookup services on the Internet include DNS and directory services. CHORD has some desirable properties, including scalability, provable correctness, and reasonably good performance that's also fairly easy to reason about. The main motivation of CHORD is scalable location of data in a large distributed system. So a publisher might want to publish the location of a particular piece of data, such as an MP4, with a particular name, such as Annie Hall. It needs to figure out where to publish this data in a place that the client can find it, so that when the client performs a lookup for Annie Hall, it's directed to the right location that is hosting the data. The key problem that we need to solve here is lookup, and you can see that the function that needs to be provided is just a simple hash table. But the thing that makes this problem interesting is that the hash table isn't located in one place, but that it's distributed across the network. So what we're trying to build is what's called a distributed hash table, or a DHT. The way that we're going to build this is using a mechanism called consistent hashing. In consistent hashing, the main idea is that the keys and the nodes map to the same ID space. So what we're going to do is create a metric space, such as a ring, and we'll put nodes on this ring, and the idea is that these nodes each have some ID. Now the keys should also map to the ID space. So in this case, just for the sake of example, let's suppose that we have a 6-bit ID space. So IDs might range from 0 to 63. Now you can see that the nodes have IDs, and the keys also have IDs in the same space. A consistent hash function will assign the nodes and the keys an identifier in this space. A hash function, such as SHA-1, might be used to assign these identifiers. In the case of nodes, the ID might be a hash of the IP address. In the case of keys, the ID might simply just be the hash of a key. Both of these hash operations create IDs that are uniformly distributed in the ID space. The question now is how to map the key IDs to the node IDs so that we know which nodes are responsible for resolving the lookups for a particular key. The idea in CHORD is that a key is stored at its successor, which is the node with the next highest ID. So for example, the key corresponding to the key ID of 60 would be stored at the node with the node ID of 1. Similarly, for the key with the key ID of 54. 42 would be stored at the node with the node ID of 43, 17 at the node with 32, 7 and 5 at the node with ID of 10, and so on. Consistent hashing offers the properties of load balance because all nodes receive roughly the same number of keys, and flexibility because when a node joins or leaves the network, only a fraction of the keys need to be moved to a different location. You can actually prove that the solution is optimal, meaning that the minimum number of keys need to be remapped to maintain load balance when a node joins or leaves the network. Let's talk a little bit about how to implement consistent hashing. One option is for every node to know the location of every other node. In this case, lookups are fast. In fact, they're order 1. But the routing tables are large, in particular because every node needs to know the location of every other node in the network. The routing table must be order n, where n is the number of nodes in the network. So for example, if node 32 wanted to look up the location of Annie Hall, that value might hash to 60. And if every node maintained a routing table entry for every other node, 32 would know that the key corresponding to ID 60 was located at node 1. So the lookup would be order 1, but the table would be order n. Another option is that each node only knows the location of its immediate successor in the ring. So for example, node 32 would know the location of node 43, but of no other node. This results in a small table of size order 1, but locating the content, as before, would require order n lookups. So in summary, if every node knows the location of every other node, then lookups have good performance at the expense of larger tables. If every node only knows its successor, then routing tables can be small, but every lookup operation is order n. A solution that provides the best of both worlds is called finger tables, where every node knows m other nodes in the ring, and the distance of the nodes that it knows increases exponentially. So for example, node 10 would maintain mappings for 10 plus 2 to the 0, 10 plus 2 to the 1, and so forth, where finger I points to the successor of n plus 2i. So finger 0 would point to the successor of 11, which is 32. Finger 1 would also point to 32, and so forth. Finger 5 would point to 43. Now every node knows its immediate successor. So what we want to do is find the predecessor for a particular ID and then ask for the successor of that ID. So let's suppose that node 10 wanted to look up a key corresponding to the ID of 42. It can use the finger tables to find the predecessor of that node, which in this case is 32. Its finger tables have the mapping of that node's location as well. It then can ask node 32 for its successor. At this point, we can move forward around the ring looking for the node whose successor's ID is bigger than the ID of the data, which in this case is node 43. Due to the structure of the finger table, these lookups require order of log n hops. This results in efficient lookups, order log n messages per lookup, and the size of the finger table is order of log n state per node. Another consideration that we have to take into account is what happens when nodes join and leave the network. When a new node joins, we first have to initialize the fingers of this new node. Then we must update the fingers of existing nodes so that they know that they can point to the node with the new ID. And finally, the third step is to transfer the keys from the successor to the new node. In this case, the key that we must transfer from the successor, 1, is the data with ID of 54. In this case, each node's successor is maintained, and the successor of any particular ID k is always responsible for k. A fallback for handling leaves is to ensure that any particular node not only keeps track of its own finger table, but also of the fingers of any successor, so that if a node should fail at any time, then the predecessor node in the ring also knows how to reach the nodes corresponding to the entries in the failed node's finger table.